Hello, my name is Faith Chung, and this is my presentation for CS598, Deep Learning for Healthcare. So the problem that's being solved by this paper is diagnosing someone with sepsis early on. And the motivation for this problem is that early diagnosis is necessary because when the infection goes too long, it could cause the patient to die. And the symptoms and the costs are very severe. However, the early signs are really similar to common illnesses like the common cold, like fever, chills, rapid respiration, high heart rate, etc. So basically, the researchers trained a deep learning model to take in time series EHR data, which mostly consists of vital signs that are taken at each time step while the patient is at the hospital to diagnose someone with sepsis early on. So what exactly was their solution? Well, this is the architecture of their deep learning model. So it's basically a bi-directional LSTM where the inputs are the input time series data. So each set of features for each time step are first weighted with the attention mechanism, which are then turned into an embedded vector. And also the length of stay of that patient is turned into a time encoding. So that embedding and the time encoded are concatenated together and passed into the LSTM. Once the bidirectional LSTM is run, you get the hidden states for each time step, and a global max polling is done across all the hidden states to get the max values for each index in the hidden state vector, and that's passed into a fully connected layer, which results in one output, which is then put into a sigmoid activation function, which gives you the classification of whether or not, or the probability of whether or not someone has sepsis. So that's their approach. So to summarize, they apply an attention mechanism to the input features to weigh, more important features than others. That's then embedded and concatenated to a time encoding, which is then passed into the bi-LSTM. And then there's a global max polling for all the hidden states, fully connected layer, sigmoid activation function, and then the result. So what was my reproduction attempt? Well, first off, I implemented two baselines. The first one is a logistic regression. The second one is a naive LSTM without any of the extra components discussed before in the paper. And both of them performed pretty well within 1% of that which was stated in the paper, so around 0.86 for the AUC. I then implemented this proposed model with all the components, and I implemented 4 ablation studies. So I basically got rid of one component at a time and then ran the model and checked to see how important that component was in the overall model's performance. So you will see 4 ablation studies in my Jupyter notebook in my Git repo, one for each component. So the embedded vector, the time encoding, the global max pooling, and the attention mechanism. So yeah, that's my project. Feel free to check it out in my Git repo. Thank you.